Cisco Certified Network Associate Day 6. Welcome back everybody. I'm Imran Rafa, your trainer for this entire series. Before we start today's episode or today's video, I first need to thank each and every viewers on YouTube who has made my video very popular. About 8 months ago when I started this series, I did not think the success that this video series is going to get, and I'm really humbled. Just to show you all, my channel NetworKing has crossed about 300,000 views, so it's about 312,724 views as of today. We have about 11,208 subscribers, and I haven't even in my dreams imagined that this humble beginning would reach such great highs. So firstly, I would like to thank each one of you who is coming onto the channel and viewing my videos. Thank you from the bottom of my heart. Alright, without wasting much time, let's get straight into today's class. Today we would be filling in those gaps that has come in the last 7 videos. Though today is day 6, technically we have already put 7 videos online, so this will be the 8th video. That is, we have day 1, day 2, and day 3 is broken into 3 different videos. So you have day 3 AM, day 3 PM, and day 3 LM. Then we have day 4, day 5, and today is day 6. Right, without wasting much time, let's get straight into today's video. Today we would be dealing with 3 important topics. The first one being DHCP, then we would look into TCP transmissions, and then we will look into common port numbers. Right, so we spoke about IP addresses, and one critical factor in IP address configuration is DHCP. Now the full form of DHCP is Dynamic Host Configuration Protocol, and what it literally means is it's a protocol that helps you configure IP addresses to host dynamically, right? So we have all seen this screen. So when we click on the option obtain an IP address automatically, what it literally does is it actually sees or searches for a DHCP server that is configured in the same subnet, and it sends different packets and requests for an IP address. DHCP has 6 messages, of which 4 are critical for assigning an IP address. The first message is the DHCP discovery message. Now DHCP discovery message is like a hello packet. Now what I mean by saying hello is when a new device comes onto the network, the device literally asks or shouts out in the network asking if there is a DHCP server around. So like you see on the screen, it's like a broadcast. It's a shout to the DHCP server. Now this shout, like I said, is a broadcast, so all the devices in the network hears this broadcast. Now if there is a DHCP server, what it does is it sends a DHCP offer packet. Now DHCP offer packet is where the DHCP server replies to the DHCP discovery that the client sent by telling the DHCP client to take a certain IP address. Now what the DHCP server does is it reserves an IP address. Let's say in this case 192.168.1.2. It reserves it. It doesn't give it. It reserves, saying okay, I'm offering this for somebody. And it tells it also in that packet, DHCP offer packet, it also tells his IP address. Now if there are more than 1 DHCP servers configured in this network, even the other DHCP server would have got the broadcast from the client, and he too would offer an IP address, like in this case 192.168.1.50, and it would tell that the server's IP address is 192.168.1.200. Now ideally we wouldn't configure 2 DHCP servers in the same network, but sometimes it happens, right? So when this DHCP offer is sent back to the client gets 2 DHCP offers. Now it's up to the client to decide which DHCP offer it wants to accept. So let's assume that it wants to accept the first one. So what it does is it sends a DHCP request packet. Now, the DHCP request packet says, okay, I will take 192.168.1.2 offered by DHCP server 192.168.1.1, right? Now that's again sent back to the network, and the DHCP server hears that. Now, when DHCP the DHCP server at 192.168.1.1 hears that, he says, all right, I acknowledge that. So he sends a DHCP ACK to that. The other DHCP server, what it does is it had reserved the IP address 1.50, right? So what it would do is it would put that IP address back to the pool, so it could assign that IP address to another client if there is another request. So these are the 4 critical messages that the DHCP exchanges in the initial DHCP IP address assignment. Now, DHCP also has 2 more messages, that is the DHCP information message. The DHCP information message is issued by the client if it needs more information than the information that is provided by the DHCP offer. That was the second step. So in the DHCP offer, if the server had not given enough information, or if the client needs more information than the information that was there in the offer packet, the DHCP information is what is sent to obtain those extra information. There's one more message, the DHCP release. Now, DHCP release is the message sent by the client to the server to tell that it wants to release the IP address that it already has. But most of the time what happens is the user just disconnects before the client can send that message to the server, right? So before the client can even send that message, either the computer is shut down or the computer is disconnected. Now that's up to the user, right? It's up to you and me for us to just pull the plug. But the client, the machine, your computer, your laptop, whatever, it doesn't have enough time for it to send a DHCP release message. So in the DHCP process, DHCP release is not a mandatory step, right? So the mandatory steps are DHCP discovery, DHCP offer, DHCP request, and DHCP acknowledgement. So that is how an IP address is configured. Now, when you talk about DHCP, I need to also say that DHCP is configured, as we will learn in maybe one of our future videos when we create a DHCP pool. But normally when you configure a DHCP server, you would tell the DHCP server what is the pool. The pool, what I mean by pool is you tell the DHCP server that you can assign IP addresses, let's say from 192.168.1.1 to 192.168.1.254. So the DHCP server will assign IP addresses only from that pool of 254 IP addresses. So this is something as an administrator you and I can configure. Right, next we'll look into TCP transmission. Now, I don't know how many of you know what this tin can phone is, but when we were young, we used to run around and we used to make these tin cans. We used to put a string and then we used to talk to each other, right? That's how our childhood was. But unfortunately, today's children don't have the luxury, I would say. I mean, today children are in front of the TV right from, I think, age 1, they are in front of the TV. They play PSP and they really don't, I don't know, maybe that's debatable, but I think we had a better childhood. We really went out and played. But today the children are couch potatoes, and I have a 1-year-old boy, and I don't know, I can already see that he's addicted to the iPad. And I mean, he's too small, but I don't know, somehow I think today's kids are born with with that knowledge of how to use electronic devices. So anyway, that's a debatable topic. But what I was trying to say is, when we were young, when we were playing, we used to make these tin cans, and when we tie this string and we talk from one end, the other person could hear, right? So that's more like a connection. Now, even for a TCP transmission, there need to be a connection that needs to be established before the real transmission can start. Now, like we discussed in one of our previous topics, TCP is a connection oriented transmission, whereas UDP is a connection less transmission, right? So UDP UDP is like saying that I will throw the ball and it's up to you to catch it. Now whether you're ready or not, that's not my problem. I'm going to throw it. But TCP is more like you communicate, you talk to the guy and you tell, you know what, I'm going to throw the ball, and you have a discussion, you have a connection, and then you throw the ball. So he's ready to accept that, right? So compare that to what happens in TCP. It's like the TCP actually builds a connection, then it starts doing the real transmission. Now how does it build that connection? It built that connection by going through what we know as the three-way handshake. Now it's a technical term. I know it looks very very non-technical, but three-way handshake is actually a technical term in TCP communication. So three-way handshake is initiated by the sending device. So now how it does that is by creating a sync packet. Now this device, so let's assume that this girl whose face you can see, we call it device A or the girl A, and the girl who you cannot see the face, that is girl B. So A sends a sync packet to B. So the sync packet goes to B, B receives that. So B says, okay, somebody wants to communicate with me. Now I need to also tell them that I am ready for it. So how do I say I am ready for it? I would send another sync packet. But instead of sending the sync packet and then an ACK, acknowledgement for the original sync packet, for this packet, so instead of sending an ACK separately for this sync packet, what it does is it combines a sync and acknowledgement in one packet and it sends through the network, right? So at this point, device A's sync is sent and he's received, or she's received, in this case, she's received a ACK for that. Now device B has sent a sync. Now device A has to send an acknowledgement back. So what it'll do, it'll just send an acknowledgement back, right? So at this stage, device A has sent a sync and received an acknowledgement and also received a sync. Device B also has received a sync and it also received an acknowledgement. So both of them have received a sync from the other device and an acknowledgement for his or her own sync message. Now at this stage, we say the connection has been established, or this is the basic three-way handshake in a TCP transmission. Next we will deal with TCP transmissions windowing technique. Now what is windowing technique? If you've tried, now especially in Windows, if you've tried transferring a big file from one drive to another drive, let's say a 2 GB file, initially it would come back and say, alright, this transmission is going to take about 1 year. And you would say, wow, 1 year. And then few seconds later it says, oh wait a minute, it's not 1 year, I think it's about 6 months. After some time it's going to say, wait a minute, I think maybe I can do this in 1 month. And then after some time it comes back, 1 day. Then few seconds later, 6 hours, 3 hours, 1 hour, 20 minutes, 10 minutes, 3 minutes. So finally it stops at 3 minutes, and that's exactly the time it takes. It's going to take 3 minutes for the transfer of those files. Now what happened? So initially when your device tried to communicate with the other device, it sends one packet. Now it sends one packet and it waits for a acknowledgement, right? Now it sends that packet and it waits for a long time for the acknowledgement. So it says, okay, if at this speed, if I have to complete this entire 2 GB of data, it's going to take about 2 years. Now after some time it receives the ACK. Now it thinks, alright, I've sent one, I've received the ACK. That means it's perfectly fine. The receiving device is capable of receiving 1. It says, okay, let me try sending 10 instead of 1. So it sends 10. After some time it sends, the ACK for 11. So that's how it works. If it receives 10, then the receiving device will send the next message. So let's say if it has sent the 10th packet, then it says ACK 11, which means that it is expecting the 11th packet. Now the sending device says fine, he sends maybe 100 packet this time, and the receiving device says I received it, I am expecting 101 now. So as time goes by, it increases the number of packet that it is sending. Now that is exactly why you see that time dropping from 2 years to 1 year, 6 months, because every time it is doubling or it's increasing its capacity of how much it is transferring. Now it will reach a point where, let's say it would have sent 10,000, but the receiving device buffer can only take about 9,000. So it would say, all right, I received 9,000. I'm expecting now. I'm waiting for the 9,001 packet. And that point, the sending device realizes that, all right, the receiving device buffer is that. I mean, its buffer capacity is only 9,000. So it will constantly start sending 9,000 packets, and that is about the time when the time in like in the example of the file transfer, where the time would have come down to 3 minutes, and 3 minutes is constant because now the both of them have established and realized what is the capacity. Now that is exactly what windowing is. It is one of those flow control mechanisms where both of them gradually, by doing this, it realizes what is the capacity of the transmission. Now there might be a question, somebody might ask, why can't they negotiate that earlier, or why don't you already know this is the capacity of that device? Now that's not possible because there are various types of devices on the network. So you will have an iPad, maybe iPad's capacity of transmission is different. You might also have an iPhone, capacity is different. You might have different types of phones, or maybe you have a very old computer. So everybody has got different capacity of network transmission. So depending on that, when they do this, when they start doing something called windowing technique, so they start with a small number, then they keep increasing that window. So you send 1 packet, 5 packet, 10 packet, 1,000 packets, 10,000 packets. You slowly sliding that window to make it bigger and bigger until it reaches a point where that is the maximum they can send at any one point of time. Right? So that's another concept called windowing that is also part of the TCP transmission. Next we'll look at the common port numbers. Now this is a classic situation, a classic scenario where you have one server, maybe that's a data center, right? So it has a file server, web server, email server, DHCP server. Now if a device communicates with that server, like for instance this red data traffic that was going, that was a file server traffic, so that was going to a particular port or particular application, a particular server. Now how did that server know which server this traffic was supposed to go? It knows by looking at the destination port number, right? So there are standard port numbers in every transmission. If you look at the frame, there is a place where it mentions the destination port number. It also gives a source port number. Now source port number is required for it to send back. Now like in this case, there is a blue traffic. Now blue traffic is a web traffic. Now both of them, blue and red, goes to the same server or same physical server, which has different servers installed on that. So maybe it's, like I said, it's a data center, it's virtualized, so virtual servers. Now how did it know that the red traffic had to return back to this IP address? They know this by making use of port numbers. If you go to this website in Wikipedia, that's a very good website. It lists all the standard port numbers. Now let me just show you that. All right, this is a beautiful website. Now if you look at it, it has all the port numbers listed. Now let me just scroll down. Wow, that is a big list. Okay, that goes up to some 61,000. Port numbers can go from 1 to 65,565, something that range. The port numbers from 1 to 1024 are known as the well-known port numbers, right? So you have port numbers like 21 TCP FTP, 22 is SSH, 23 is Telnet. Then we have port 80, very popular port. TCP port 80 is HTTP. TCP 443 is HTTPS, which is like the secure version of, sorry, this one. HTTPS is secure version of HTTP. So some of the ports, TCP and UDP is the same thing, but some of the port, for instance, port 80 TCP port 80 is different. TCP port 80 is HTTP. UDP port 80 is again HTTP, but it's different HTTP. So just because a port number is something in TCP, don't always assume that UDP also it's going to be the same thing, right? So you will not need to by heart this entire list. Of course, it's practically not possible to by heart this entire list, but some of those popular and well-known port numbers, it's best to remember, right? And like I said, some of them are official port numbers, which that means there is an RFC and there's a standard, and some of them are not official, like Chromium. They say UDP port 80 is quick for Chromium, for HTTP, I don't know, but something, it's an unofficial port. So there are so many common port numbers, and port numbers is what enables this traffic to go and come back and be delivered to the right applications, right? So now let's look at a data flow through our network with whatever little information we know so far. So let's assume that this computer 10.1.1.10 wants to communicate with this computer or this server, this file server at 30.1.1.10. Now whatever you see below that in XXX, that's the MAC address. Now I have put the MAC address with only the last 4 hexadecimal numbers, because I mean this is an example. Normally it is a 48-bit number, hexadecimal number, with 12 hexadecimal numbers. So each of those hexadecimal number is 4 bits long, so it's a 48-bit number with like I said, with 12 hexadecimal digits, right? So if this device wants to communicate with this server, first, like we know, part of the 3-way handshake, it has to send a sync. So it creates a SYN, it puts a source port number. Now what's a source port number? Source port number is a port number that is dynamically generated by Windows. Now Windows will just randomly take a port number between 1 to 65,000. Mostly it is going to be in the upper part of that 65,000, because the lower 1 to 1024 is a well-known port number. So it will not use those 1 to 1024. Normally it will be 25,000 plus port number. So that it will create a random source port. Then it will create a destination port number. Now in this case, the application whichever is trying to connect to this FTP server knows that it needs to send an FTP traffic, right? So it says the port number is port 21, right? So then it says, okay, my IP address is 10.1.1.10. I need to go to an IP address of 30.1.1.10. This forms the packet. Now this packet does not change until it reaches the end of this communication. What we need to understand is, one of the things that I want you guys to take from this video is to see how the data goes in through the networks. So when this computer sees the source IP address and the destination IP address, it realizes one thing, that this IP address is not in this local network. Okay, one more thing that I haven't told is these are all /24 IP addresses. So if you look at /24 IP addresses, one shot the computer realizes that this 10.1.1.10 and 30.1.1.10 is not in the same network. So it realizes that for it to go out of this network, it needs to go to 10.1.1.1, which is the gateway and which is connected to which is configured at one of the interfaces of the routers, right? So it knows that it has to go to 10.1.1.1. So it knows that its MAC address is something at 111, but it does not know the MAC address for 10.1.1.1. What does it do? Yes, it sends an ARP request. Now ARP goes as a broadcast, everybody in the network receives, but only the router with the IP address 10.1.1.1 would reply. Now he replies with his MAC address, which is AAAA. What that device would do is put that in that frame. Once that frame is ready, just before it goes out of the network, it would do something called as the frame check sequence, or CRC. It's just it's a error checking, error detection mechanism. So what it literally does is it takes this entire thing from sync to this MAC address, puts it through a hashing algorithm, let's say an MD5 hash. So it just puts through a hashing algorithm. It gets a hash value. What it does is it just attaches that hash value to the start of the frame. So you have an FCS. FCS is frame check sequence, or CRC, which is cyclic redundancy check. Now some people say FCS, some people say CRC, so I've just put both there, but it just a hash value. That's all it is. It is there to make sure that whatever data is coming through the network is error free, right? So when this data or frame goes through and reaches the router, the first thing it would do is it would take this FCS or CRC value, take whatever is remaining, put it through the same hashing algorithm, and see if the hash that is generated by it is the same that came with this frame. Now if this FCS matches the FCS generated by this router's interface card, brilliant. That means that there was no error that was induced during transmission, right? The next it looks at the MAC address. It says, okay, MAC address AAA, that means it is addressed to me, and it strips that away. Next it looks at the IP address. The minute it sees the IP address destination is 30.1.1.10, it realizes that this packet is not to the router, but it is going through the router, right? So what it does, it says, okay, I need to see where 30.1.1.10 network is. Now I know we haven't covered, or we haven't reached the routing concepts, but just know that routers would have a routing table, and in the routing table there would be entries for this network 30.1.1.0. remember, it is not the host IP address that is going to be there, but it's going to be the network ID, right? So it would say 30.1.1.0/24 is reachable by going to 20.1.1.2, right? Now you might ask, how does it know that? Just know for now that it knows. Either it could be, or automatically learnt by using routing protocols, or maybe as administrator you configured it there as static route, right? But either ways, this router's routing table will have that entry there, right? So it knows that it has to send this packet to 20.1.1.2. now assuming that this packet already knows the MAC address, we will continue from here. But even if it doesn't know, then it will run a ARP again. It will try to get the MAC address of 20.1.1.2, and then it will continue. So we are assuming that it already knows the MAC address, so it will put a source MAC address as BBB, destination MAC as CCC. It again does the same computation or hashing algorithm with this entire packet, and puts the hash value at the start of the packet, right? Then it sends that frame across the network. It goes to the device. It again removes the FCS value. It checks, it does a hashing, and it checks if whatever data it received is not corrupt. Now as when the FCS matches with the hash that the device generates, it deduces that the data is good. Then it removes the MAC address again, and it looks at the destination. It sees it is 30.1.1.10, and it knows 30.1.1.10 is connected to its interface, right? So it sends again, it does the same process continues. It finds out the MAC address, it puts those MAC address, does the hashing, check and attaches the hash to the frame, and sends it across the network. So when the receiving device receives that, it again does the same thing. It checks if that hash is matching, and if the hash is matching, it knows it did not have any error that was induced. Next, it will remove the MAC address from the table. It will remove this protective cover, which I put there for reference to tell you that it never changes throughout the journey from the start till the end. It looks at the IP address, and it realizes that it is the destination. It is the destination this packet was supposed to go, so it can strip out the MAC address, to the IP address information, which is layer 3 information. Then it looks at the port numbers. It says it has to go to port 21, and it knows that it's port 21. It knows it is an FTP traffic, and also it looks at sync. So it realizes that somebody is trying to establish a connection. Now what it has to do, according to what we know, it will create a SYNAC packet. It will reverse this whole process. It will send that back to 10.1.1.10. This device 10.1.1.10 will create an ACK, will follow the same process as we did in this slide, and send that to this device. Once that happens, the connection is established. Now, one thing you need to know is that all this happens in less than a second. So it's very, very fast. It is just that we have tried to slow this process to show you exactly how it works. This is something that we have learned, and I think it has been really useful. What I hoped with this video is that we could fill all the gaps that we had with whatever we learned so far. So if you have any questions so far, please write into me at imran.rafai@nwking.org, or better, you could just post your questions below this video. What I'm going to do from next video onwards is going to pick 3 best questions from YouTube, and I am going to address at the end of every video from now onwards. I will have a section which says the best question. So I'm going to put that question with your name, and I'm going to answer it in the video. So what it's going to do is, if I think a question is going to help a lot of people, I think that question should go in the video, and I will answer it live, so everybody gets benefit, right? So it is also your opportunity to go in one of my videos. So guys, start writing to me, put all your questions down there, ask some intelligent questions, and I'm sure a lot of people are going to benefit with that. Thank you so much. Thank you for following. Thank you for subscribing. And for those people who have not yet subscribed, please click on that red button, subscribe to our video, because it is also going to notify you every time I put a new video. So thank you once again, and have a wonderful day.